A very warm welcome to more than 400 registrants of our webinar Decoding Decibels, a deep dive into acoustic camera applications for building acousticians and environmental noise professionals. This run on our webinar more than underlines the importance of this topic for professionals like you. Before we dive into our presentation, let's take care of a few housekeeping items. Throughout the presentation, if you have any questions, please type them into the question box in your Zoom control panel. I'll be monitoring them and will address them during the presentation. We'll also have dedicated time at the end for further questions. Now to address some common points, you'll receive the slides from today's presentation afterward. This webinar is being recorded and you'll receive a copy within the next 24 hours. Your feedback is also crucial to us. Please take a moment to complete the exit survey at the end of the webinar and let us know how we can improve our program. So with that out of the way, it's time to formally introduce ourselves. My name is Robert. I am the Chief Growth Officer here at sevenbel. Together with me on the panel is Thomas, the founder and CEO of sevenbel. And before we jump into the heart of our discussion, let's take a moment to set the stage and talk about how we'll be spending the next 45 minutes together. Our journey begins with a brief introduction of our acoustic camera, the soundscanner. All measurements that we present today were performed with this disruptive device. Then, without further ado, we will turn the time over to Thomas, who gets into the practical side of things. He'll explore how acoustic cameras are used in real-life situations. And we'll see how top-notch acoustic cameras are helping professionals like you solve problems and improve sound quality. And finally, it's obviously your turn. If you have any questions or thoughts, feel free to ask. Whether you're curious about a certain application or want to know more about how to use acoustic cameras in your work, we're here to help. Our acoustic camera, the soundscanner, harnesses the patented sound field scanning technology. With only 5 microphones, we scan the incident sound field at over 400 positions, thereby processing minimal data compared to conventional cameras. And this innovation eliminates bulky and costly equipment and computes acoustic images in the cloud for the first time. The streamlined design consists of a tripod with fixture, a turning sensor, and a mobile device, all wireless and battery powered. The mobile device software is tailored for troubleshooting, ensuring high responsiveness, clarity, and user-friendliness. You can intuitively access function through familiar mobile app gestures like swiping, pinching, and tapping. Moreover, we provide a range of advanced software features for post-processing data on desktop computers. Additionally, the soundscanner offers remarkable mobility, perfect for fieldwork or construction sites. Encased in a compact carrying case, the sensor weighs just over 1 kilogram, making it effortless to transport upstairs, load into vehicles, or take on trains or airplanes. So now, without further ado, I'll pass the floor to Thomas, who will demonstrate how our top-notch acoustic camera are empowering professionals like you to solve problems and enhance sound quality. Thomas, floor is yours.
All right, thank you, Robert. Let's dive into building acoustics. Now, one of the key tests in building acoustics we run is the sound transmission measurement. It's a standard measurement we use to quantify what level of sound per frequency band is transmitted between rooms or floors in a building. And to do this test properly, we use a Class 1 sound level meter along with either an omnidirectional speaker or a tapping machine. And these tools help us to get a clear picture of whether a building structure meets regulations or not. If the building structure falls short, there is some detective work to do, and we have to identify the root cause for the lack in transmission loss. It could be factors like how heavy the interior partitions are, how much sound they absorb, how stiff they are, and how well they damp. Then there's things like how well the walls are decoupled and if sound is bypassing the structure. Also, little gaps or holes in the structure are like tunnels for sound, and especially at medium to high frequencies. So let us now take a closer look at the real-world application. Here we have a contemporary building with a glass facade all around and a meeting room with a capacity of 10 people on the left, as well as a small office space with a capacity of 4 people on the right. The interior partitioning has been retrofitted when a new company renting that portion of the building moved in. And soon after, people in the office space started complaining about discussions heard from the meeting room affecting their productivity. This obviously is a well-known use case and calls for a sound insulation measurement of that interior partition. Here, in this case, the omnidirectional speaker is set up in the office space or send room, and the sound level meter and the acoustic camera is used to capture the transmitted sound in the meeting room or receive room. The sound insulation measurement reveals deficiencies in the 500 Hz up to the 1 kHz third octave band. And let us now look at the results that we get when trying to localize these deficiencies with the sound level meter and the sound scanner. In the image on the left, we see a perforated ceiling, some HVAC installations, and the interior partition joining the frame of the glass facade. Of course, we all know the limitations of measuring sound pressure levels in corners, close to the floor or ceiling due to reflections. And also, we influence the sound field with our physical presence. And these levels can fluctuate depending on where we stand. We record the sound pressure levels now on the surface of that interior partition. And we see elevated levels of around 58 to 60 dBA as we measure along the perforated ceiling, as well as along the frame of the glass facade. And now the question arises where that weakness is exactly. Is it the corner? Is it along the frame? Or somewhere in the area of the perforated ceiling? As a comparison, now let us see what result we can achieve with the sound scanner. In the acoustic image on the left, we clearly see that the dominant sound emission is coming from the left panel of the perforated ceiling, and we can also locate a reflection on the window which originates from the source on the ceiling with a sound pressure level that is 6 dB below. And the next obvious step is to open that ceiling panel and look what is underneath. And the image on the right shows a cable feed-through, which is obviously not insulated and causes a severe breakdown in transmission loss. So what can we now derive from this first application? Clearly, the sound scanner supports you in identifying the root cause in sound transmission issues unambiguously, especially in complex acoustic situations where sound level meter data may not be fully conclusive. In fact, the sound scanner lets you separate direct sound from reflections. And these results help you to not only step up your productivity, but also gain confidence in situations which require costly follow-up investigations and rework. You can communicate and document your conclusions based on acoustic images, which are also easily understandable for people you're working together with and who do not have the same level of experience in building acoustics as you have. And on top of that, the sound scanner complements your portfolio of existing building acoustic tools, like your sound level meter, omnidirectional source, and tapping machine, and lets you cover new applications, as we will see later on as well. Okay, so now let us talk about applications in the field of noise control and environmental noise. Implementing noise control measures for industrial plants, of course, involve the measurement of sound emissions at various points of observation. And that data is eventually fed into computer-generated models. And based on that, the model is modified accordingly with planned measures like noise barrier, a silencer, etc., to compute the effectiveness of these proposed solutions. The challenge with such an approach is to find the right level of detail in these models. So how many measurements at different points of observation or even along the facade of a plant do I take to come up with a model predicting the sound field that is close enough to reality? Also, in many real-world applications, the access to critical sound emitting areas is difficult. And it is, I think, fair enough to say that making the right assumptions for these hard-to-access areas is far from trivial. As we all know, these measurements can take up to multiple days to cover a reasonably sized plant, and it may be difficult to ensure that the measured sound levels at the various positions are consistent due to varying operating conditions throughout the day. In the end, these measurements are simply time-consuming and complex. So let us now take a closer look at how we can leverage the acoustic camera for finding the right level of detail for an acoustic model of a plant. The object in this case of interest is a 14-story production building, which exceeds regulatory limits, especially during the night. The plant operator in this case is required to implement measures since an expansion of the production area is not improved unless the measures for noise control are implemented. The sound scanner in this situation is set up at 3 distinct positions to get a basic understanding of the dominant sound emissions from that building. Measurement point 1, for instance, is on premise and shall capture the sound sources in the near field close to the building. Measurement point 2 is outside the company's premises in front of a sound barrier. And measurement point 3 is at a distance of about 120 meters away from the building in direction of a residential area. The broadband acoustic images, starting from 250 Hz up to 6 kHz, in this case with a dynamic range of 10 dB, from the loudest to the most quiet source, are now shown on the right. For the on-premise measurement, we see that sound emissions are dominated by the air intake on the left and vehicle noise from a warehouse area on the ground floor. On the top floor of the building, a packaging machine produces noise that is 10 dB below the dominant sound sources on the ground floor. The situation, however, changes drastically when we look at the measurement point that was taken in front of the noise barrier, so measurement point 2. Here we see the noise from the ground floor bending over the noise barrier, and the sound source at the top floor from the packaging machine is now the dominant source. Another viewing angle is taken at measurement point 3, and it now indicates that the ground floor noise is the most dominant, while the packaging machine does not radiate that well into this direction, which is aligned with the residential area. So what conclusions can we now draw from these 3 measurements that only took us a total of 20 minutes? The air intake and loading zone noise are critical under viewing angle number 3, as this noise propagates to the residential area. And a noise barrier is, in this case, highly recommended, and its effectiveness can already be seen from the measurement under viewing angle number 2. The sound transmission of the packaging machine at the top floor of the building is caused by a weakly insulated wall, which only contains 2 metal plates sandwiched with some damping material. Going further, this information can now be used to feed a reduced acoustics model of the plant to evaluate several measures on the ground floor and on the top floor. So let us again briefly wrap up the benefits that we see when using an acoustic camera for noise control applications. First off, the acoustic camera supports you to identify the sources that really matter in order to feed a reduced acoustic model representing reality well. This, of course, saves time in the generation of that model, and most importantly, the acoustic camera provides you with a deeper understanding of how sound sources are distributed when measured at a specific point of observation. Last but not least, you are now in a position to document the effectiveness of measures very transparently by showing acoustic images. Let us now finally turn to our third and last application from the field of room acoustics.
Thomas, sorry for interrupting you. We're just having the first question coming in. I think we should make this as much interactive as possible. If you allow, I read the question, would you concur that in your example, the packaging machine noise emission is highly directive in nature, possibly at high frequency? Let me know if I should repeat it.
Perfectly understood. Thanks very much.
Okay.
So of course there's much more data behind that measurement that we took, and it's perfectly correct that that particular machine was emitting noise in the frequency band between 1.5 and 3 kilohertz. And due to the fact that the facade or that wall was essentially excited by the packaging machine, there's also some directivity associated with that. Essentially, the facade acting like a loudspeaker and predominantly radiating in a direction that is transverse to the facade of the building. So that's perfectly correct that in front of the noise barrier and by directly looking at the wall, that noise emission from the packaging machine was very dominant. And when viewed from an angle at like 90 degrees or so, there's obviously some directivity associated with that, and the reduced sound pressure level was received or perceived at under the other viewing angle that was shown before.
Thank you.
Good. Now back to reverberation analysis. The optimization of large rooms like concert halls, office spaces, shop floors, as we all know, is a very delicate thing. And again, the process involves the measurement of room impulse responses using a sound level meter and an omnidirectional source at various locations. That data, again, is eventually fed into computer-generated models, and based on that, the model is fine-tuned to reflect reality as close as possible. And based on these models, measures in the form of absorbers and diffusers can be introduced to tailor the room acoustics to a specific quality criterion like RT60, for instance. We all know that this process comes, of course, with challenges. And again, finding the right level of detail to come up with a proper model takes time and good information and estimates on material properties. And since we are dealing with large room acoustics, some locations like a roof dome are difficult to access in many situations. So overall, and as mentioned before, this is a time-consuming and very complex task. Let us now take a closer look at how we can use the acoustic camera for solving a room acoustics problem in a concert hall. Here we see the stage of a concert hall located in St. Gallen in Switzerland. And the musicians of the orchestra on the left side of the stage complain about the perceived loudness of the other instruments, especially the ones from the right side of the stage, being too high. And along with that, they also complain about hearing the delayed sound from these instruments. In a first step, we position the omnidirectional source on the right side of the stage in an area where the problematic instruments are located. And the sound scanner is set up on the left side, viewing the source and the walls and ceiling on the other side of the stage. We use a band-limited impulse as an excitation signal for the omnidirectional sound source. And the corresponding reverb time signal that is captured by the sound scanner is now shown on the bottom right. Here we are interested in 3 specific sections of that signal. The first peak is the direct sound emitted from the sound source, which happens within the first few milliseconds. Then we can see a series of primary reflections, which all happen within the first 20 to 50 milliseconds of delay. These reflections are especially critical for the perceived loudness, but not so critical for any perceived delay. The time interval stretching from 50 milliseconds to 100 milliseconds right after the initial impulse is critical in terms of the perceived delay. So let us now see how the corresponding acoustic images look like for each of these time intervals. Obviously, the direct sound from the speaker can be perfectly located. So the sound that is happening within the first few milliseconds after excitation. The primary reflections happening 20 to 50 milliseconds right after the initial impulse are mostly coming from the diffuser wall and a little bit from the left side of the diffuser ceiling. And the critical reflections, the ones that determine the perceived delay, are coming off of the wall and the diffuser ceiling. So what conclusion can we now draw from this very simple measurement? And what measures can we now easily try out? Absorbing material, for instance, can now be introduced in the areas where primary reflections are visible in order to reduce the perceived loudness. And the wall area between the diffuser wall on the bottom and the diffuser ceiling can be treated to impact the perceived delay. Of course, we need to mention at this stage that the whole setup can be made more realistic to mimic a situation with chairs and people being present on stage, and also the excitation signal can be filtered to the emitted spectrum of the music instrument of interest. Still, it's pretty clear what benefit an acoustic camera can bring along in this type of application. Primary and critical reflections can be isolated and located, and the user gets a very good understanding of how portions of the reverb signal propagate in space. For existing building structures, troubleshooting can be easily conducted without having to go through the process of measuring room impulse responses at a multitude of locations and derive a room acoustics model from that data. Again, the acoustic images help you to lead the discussion and communicate the results. And the effectiveness of your solution can not only be documented in terms of sound pressure levels, but also in the format of acoustic images that show the mitigation of unwanted sound propagation paths. So this was just a very brief overview of 3 typical applications from building acoustics, room acoustics, and environmental noise. And we are now very much happy to go into discussions and answer any open questions from your side. Thank you very much.
Absolutely, Thomas. Thanks a lot. And let's open the floor for questions now. We have time for a few questions from the audience. It looks like we have some great questions coming in through the chat already. First one being, are the acoustic images only an indication, Thomas, where sound is coming from, or is it quantified in some way?
Yeah. So, of course, as part of this presentation, we wanted to give you an impression, what kind of information you can get with an acoustic camera. Of course, all of the acoustic images have a scale coming with them. So the color-coded images show the sound pressure level at a specific spatial location expressed in terms of dBAs.
Okay, thank you. Probably going back to the room acoustics example, question from William, what is the time position resolution for this type of reverb measurement due to the rotating array? Let me know if I should repeat it for you.
Yeah, so now we are going into the details in terms of how the measurement is conducted. You're perfectly correct in saying that our scanner is rotating, so it's somewhat capturing the impulse response at the specific orientation of the sensor. So this is why we need a periodic excitation of the omnidirectional source, depending on what the reverb time in a specific room is. So it can vary between 0.5, 1.5, 2 seconds, or even higher. But as you start spinning the sensor and as the omnidirectional source is emitting those pulses or room impulse responses are captured at different orientations of the sound scanner. And that entire data set, typically comprising a time interval in the order of 10 to 30 seconds, is then used to compute these acoustic images with a very fine time and depth resolutions. So typically we're talking about a time resolution in the order of less than 1 millisecond. And this is also required in order to track that sound propagation in space.
Okay, thank you. Then we have another question that Cesar is addressing. Thanks, this is very interesting. What is the approximate cost of the acoustic camera to buy or rent?
Yeah, so the starting price for our acoustic camera using our public cloud solution, so meaning where the measurement data is sent to the cloud and processed there, is at around 6,000 euros. It comes with a carrying case with all the components included, like one sensor. It can be either a sensor for environmental noise measurements, where you would typically require a large measurement surface, or it can also be a smaller variant that can be used in small confined spaces. All of the accessories are included. You can either choose from a smartphone or from a tablet device. Starting price is at around 6,000 euros, as I said before, and depending on what features you're adding, may it be desktop application, may it be advanced software features, that price can go up to 10 to 15,000 euros.
Okay. Fantastic to see the engagement in the chat with all the questions rolling in. Next one from Henk. The sound scanner is a two-dimensional instrument. Environmental noise issues are often three-dimensional due to plant dimensions. Therefore, a detailed acoustical model is always and almost required to analyze noise levels and equipment contributions. The scanner can be a valuable addition, but not replace the detailed model in my experience. Can you elaborate on that?
Yeah, so certainly, I hope that this came across properly. So we're certainly not claiming that that we're replacing all the tools and equipment that is available at this stage and which form the state of the art. The sound scanner in this context is a complementary tool which can certainly speed up the process in certain situations where you want to, as I said before, come up with a reduced acoustic model, which captures the details that matter. And but it's certainly not replacing or bypassing the existing process. It can be just a helpful tool for speeding up certain things and coming and having quick wins in terms of making capturing the low-hanging fruits and making quick and easy decisions.
Next one, what is the frequency range of measurement recommended? In the environmental noise case, it was between 250 Hertz and 6 kilohertz.
Exactly. So for environmental noise measurements, we typically recommend our P132 or P254 sound scanners. As we all know, the lowest frequency that an acoustic camera can resolve depends on the size of the measurement surface. So the larger that measurement surface is, the lower the frequency is that you can spatially resolve. With the P254, which has a measurement surface, or which covers a measurement surface with a diameter of 2.5 meters, the lowest frequency is 125 Hertz. With the P132, you can start resolving sound sources from 250 Hertz upwards. And At some stage, of course, there's a limitation by physics how large the system can eventually get, but these instruments are certainly applicable for this type of applications.
Okay, Thomas, probably you can go back to the building acoustics case, because we have a specific question regarding this case, and I'd like to support your statement with the picture. Building acoustics, not noise control, please.
Sorry.
Don't worry. There we go. Yeah, we need the numbers, the dBA numbers, because the question was back to the color-coded image. The numbers refer to which distance from the wall?
Okay, so the image that we are showing here was essentially generated manually. So it was actually a person holding a sound level meter in his hand and probing the surface of that wall. So those values were taken right on the surface of the wall.
Okay, so the distance is
the distance
20 centimeters.
is approximately 5 centimeters or so, 5 to 10 centimeters.
Good. Another question from Henk. Does the scanner have the potential capability to be turned into a sound intensity machine / probe? And are there any questions to develop such an application?
Yeah, so we have a very interesting follow-up webinar coming up where we go into the features and details of our desktop application. And from the beginning of this year, we offer a new feature called Map and Probe. And what this feature essentially does is you can select a specific region in the optical image or in the acoustic image and can compute the sound power for that region that you have selected. It's a very simplified computation based on assuming that the sound pressure level that you have located for that selected region is distributed across a half sphere, having the radius of the distance to the object that you are investigating. And based on that, we can compute an approximate sound power level for a selected region. So this is somewhat going into the direction of, I think, what is being addressed here. But at this stage, the sound scanner itself is an array of microphones measuring sound pressure. All of the acoustic images that we are showing are expressed in terms of sound pressure levels in dBA. But with some help of advanced processing, you can also get down to the point of computing approximate sound power levels for specific regions of interest.
Okay, a couple more questions going deeper into the feature side of the product. What about the MEMS microphones? How are they calibrated? What method of calibration is used there?
Okay, so the digital MEMS microphones are per se coming out of a semiconductor process. So they have very tight tolerances. Included in the kit is a calibration speaker, which is used for aligning the optical and the acoustic image. Along with that, it's also used for checking the so-called dynamic range of the acoustic image, and along with that, whether the sensitivity of the microphones is okay. So if there was any deviation in terms of that the minimum dynamic range is not met, then this would eventually show up in this kind of calibration measurement. Also, our firmware, which is embedded in the sensor, is constantly checking for the plausibility of signals, microphone signals, and if there was any deviation, meaning microphone losing sensitivity over time, or a specific microphone losing sensitivity at a specific position, then this would be reported to the user. Other than that, the device is maintenance free, and yeah, that's pretty much it.
Thank you. Another question that points in the direction of background noise. Can specific sources of noise be identified within the interior of a factory with a high background noise level? For example, a bottling line with a background level of 90 dBA and sources to be identified at 85. So you probably know what this is pointing at.
So the sound scanner itself has a suppression of background noise or noise not coming from the field of view of the optical camera in the order of 15 dB. So if you had two sources with equal strength or equal loudness, one in front of the sound scanner within the field of view at a distance of 1 meter, and another source in the back at the same distance, then the source in the back would be reduced by 15 dB compared to the source that is then located in front of the sound scanner. So if you had sources at equal strength, you automatically already gain a 15 dB delta. So the source that is in front of the sound scanner would certainly be the more dominant source. But if you start to approach a situation where the source that is in front of the sound scanner is already 10 dB or close to 15 dB less than the sound that is coming from the background, then these two sources are then almost at par, and the background source will be somewhat mirrored into the acoustic image. So this is certainly something that that needs to be considered when you conduct acoustic camera measurements, both inside but also in the free field outside. So when you do a sound scanner measurement inside a room, you somewhat have to make sure that you should not stand up against the wall with the sound scanner, so that any reflections from the wall would immediately hit the sound scanner from the back. Also, I think that the example that was mentioned before, if you are in a noisy production environment, you should somewhat make sure that the signal to noise ratio of sound happening in front of the sound scanner and sound or any background noise coming from the back is at least at par, or there should certainly not be a 10 to 15 dB or even higher difference between sound sources in the front and sound sources happening in the back of the acoustic camera. There are certainly other situations, where most of our equipment can also be used, for instance, for the localization of gas leaks or compressed air leaks in a production environment. In this case, you would typically conduct these measurements using ultrasound. And these measurements are typically very robust because any machinery noise would fade out at high frequencies, and you get a very robust results for localizing those sound events, even in a very noisy production environment.
Okay, thank you so much. So we're taking the last 3 questions now because we are approaching the end of the webinar. Can measurements made on broadband be further analyzed by frequencies, e.g. 200 hertz, or do you have to make a measurement in that single frequency again? Thanks.
So all of the measurements that we have shown today have been recorded over a time interval in the order of 5 to 25 seconds. And after the data has been recorded, the acoustic images will be processed, and in the aftermath, you can select an arbitrary frequency band and filter the audio signal as you like. So there is not yet another measurement or a follow-up measurement required in order to make the analysis in a different frequency band. So once you have recorded all of the data, you will get a full result both in time and in the frequency domain, and you can navigate around in these domains freely.
Very good. What is the highest frequency resolution the scanner can reach?
At this stage, we're talking about highest frequency resolution in the order of 7 Hertz.
Okay. And one question from Anton. Is sevenbel exploring the possibility of creating a scanner optimized for underwater use? This could be used, for example, to scan for noise in marine animal enclosures or tanks.
Yeah, we do understand all of these applications. There's certainly a need and a use case available. But at this stage, we are primarily focusing on building acoustics, room acoustics, environmental noise, and product engineering. And there's already a handful to do at this stage, I tell you. So these are the industries and applications that we're currently focusing on. But never say never at this stage. There may certainly be an opportunity in the distant future where we may also investigate this opportunity.
Very good.
But it is certainly doable. Yeah.
Another question regarding class 1 device. Is the device class 1 and should we have it checked by laboratory every 2 years, for example?
Acoustic cameras are in general not class 1 sound level meter devices. They are per se also not reflected in any standards or norms that you are aware of, that you use for conducting your sound transmission measurements, sound power level measurements, or other type of measurements when it comes to noise control and environmental noise. But the precision and accuracy is essentially close enough to sound level meters. There's, from a design perspective, several constraints that make it very difficult for acoustic cameras to meet the requirements of sound level meters, and this is why they cannot be certified according to these requirements and standards. And that has to do essentially with the exposed orientation of the measurement microphone that is required from the standard for class 1 sound level meters. So to make a long story short, acoustic cameras are not reflected in standards. They are not rated as class 1 measurement devices at this stage, but the values that you get can certainly be used for your investigations and can also be compared with your sound level meter measurements.
And finally, the last question. How can wind speed conditions affect your scanner measurements and outdoor source location? Very interesting question.
Yeah, so we have a couple of customers from the energy industry. They use our sound scanner in a very harsh environment, in very windy conditions, for instance, for locating sound emissions from wind turbines, from transformers, high voltage insulators in substations. And wind noise in general is, as it hits the measurement device, the signals that are captured by the individual microphones are not correlated. And per our algorithm, these signals or these disturbances are eventually suppressed and do not appear in the acoustic image. So this is why our device and along with the way we process the signals is robust in terms of wind noise.
Okay, and finally, promised the last question. The camera software limit the measurements below 125 Hertz or still showing color maps results for frequencies below 125, even knowing the reliability decreases. So basically, what happens when we localize frequencies below 125? Can you still trust in the acoustic image, or is this total crap?
Yeah. So the microphones that we use work from 20 hertz upwards, and the software allows you to select the acoustic image also in a frequency band that is out of spec. But as a user, you need to be aware of that fact that you cannot fully trust the localization accuracy at this stage. So at very low frequencies below 125 hertz, the acoustic images can at least give you an indication of whether that sound is coming more from the right, from the center, from top, bottom, or from the right. So that's certainly valid, but the localization accuracy certainly suffers as the full wavelength of the acoustic signal is not spatially sampled anymore.
Okay, thank you so much. We finally reached the end of the webinar. I'm about to start the exit poll. Kindly ask you to answer the questions just to make our program better. Thank you so much for joining in and for spending the time and taking the time to listen to